In our last video, we talked about tangent of an angle. This video will be covering sine and cosine. If you notice on a calculator, you have the tangent function right here, which we've used before, but right next to it are two others. One is cos and one is sin, and these are two other trigonometric ratios that we'll be using, and so we need to be introduced to them. The first one, sin, is sine. The second one is cosine. And the definitions are right here. Sine of angle A is defined as the length of the leg opposite angle A. And that should sound familiar. Remember, angle A is right here. Then this side is the opposite. This side is the adjacent. And this one is the hypotenuse. So sine of angle A is the opposite. Now, before we had it over the adjacent, this time we have it over the hypotenuse. So the sine of angle A is opposite over hypotenuse. The cosine, written as this, or cos when we do the function, the cosine of angle A, whatever angle A is, will be equal to the adjacent over the hypotenuse. Remember, what is opposite and what is adjacent depends on which angle we're talking about. So for angle A, the adjacent over the hypotenuse will be AC over AB. That would switch if we were talking about angle B here. So other than that, it's actually very, very similar to the tangent. So if you're comfortable with the tangent, you should become pretty comfortable with these. As it turns out, we're going to memorize these. For open note tests, feel free to look these up. Feel free to look them up for your book. But we will spend some time memorizing them, and I will expect you to have them memorized. There will be quizzes on them, just because we want to memorize these so we can free up our brain to think about other things. But for right now, feel free to just look up this chart again. The sine is equal to opposite over hypotenuse. The cosine is equal to adjacent over hypotenuse. Yeah, just look those up whenever you need that. So we'll do a few examples here. This one just says, write the sine and cosine for each angle as a fraction or as a decimal. We're going to do the nearest thousandth. So the first one here says angle D. So angle D is up top of our right triangle. We need to figure out the sine of angle D and the cosine of angle D. So the sine of angle D is equal to the opposite over hypotenuse. So in this case, 8 over 17. And when you write 8 over 17, then you'll just have to punch that into a calculator to figure out a decimal if it's asking for a decimal. So 8 over 17 is this thing. The cosine of angle D, therefore, is adjacent over hypotenuse, or 15 over 17, which again, you just punch in a calculator and get a value. So let's go ahead and try that same thing. Go ahead and pause this video for a second, just so you can get a chance to try and do part B here real quick. Pause. Okay. So for angle F, the sine of angle F is going to be, in respect to this angle, the opposite over the adjacent. So that's going to be, in this case, 15 over 17, right? Opposite over adjacent. When you punch 15 over 17 into your calculator, you should come up with 0.882. The cosine of angle F is equal to, here's angle F, the adjacent over the hypotenuse, or 8 over 17, right? 8 over 17. Punch that into your calculator, you get 0.471. So good job if you got those values. What do we notice about the sines and cosines you found? Do you think this relationship will be true for any pair of acute angles in a right triangle? Explain. So let's back up here for a second and look at those values we found. The first one, we found, we found values of 0.471 for the sine of angle D. We found 0.882 for the cosine of angle D. For the sine of angle F, we found 0.882, and for the cosine of angle F, we found 0.471. Well, that's kind of weird. these two values are the same. In addition, these two values are the same. So why is that? Let's double check this. The sine of angle D, so this angle here, is equal to the cosine of angle F. It's weird until you realize that they're basically measuring the same thing, right? The sine of angle D is measuring the opposite over the hypotenuse, or 8 over 17. The cosine of angle F is also measuring, it's now measuring the adjacent over the hypotenuse, but now the adjacent is this side. So it's again measuring EF, or this value of 8 over 17. So it's the same two numbers being plugged into both of those. So be aware of that. That property will come up. In a right triangle, triangle PQR, with PR equaling 5, QR equaling 3, and measure of angle Q equaling 90 degrees, what are the values of the sine of angle P and the cosine of angle P? I'll give you guys a second to figure that out while I draw my little diagram here. So bear with me. If you want to pause, feel free. I'm just going to make a quick little right triangle, and then I'm going to try and label it. I am a very visual person, so drawing this picture always helps me. So we have measure of angle Q is 90, so we'll put Q down here. That's Q. Sure. It doesn't matter where P and R are very much. Let's say P is there. Say R is there. PR is going to be 5. We'll use blue, sure. So that's 5. QR is going to be 3. And we know from before that this is a right triangle that's a 3, 4, 5. I think I've covered that in most classes. That 3, 4, 5 is one of those common right triangles. We could use Pythagorean theorem and solve, but that's pain. So let's just know that this is one of our magic right triangles, 3, 4, 5 triangles. And then it asks, what are the values of the sine of P and the cosine of P? So the sine of angle P here, the sine is equal to opposite over hypotenuse. So 3 over 5, sorry. And the cosine of angle P is equal to adjacent over hypotenuse. So 4 over 5. So good job. Pat yourself on the back if you figure that out. Finally, we also touched on this. Don't get too lost here on the verbiage, but notice here that it says if angle A and B are these two angles in the right triangle, then the sine of angle A equals the cosine of angle B. And vice versa, the cosine of angle A equals the cosine of angle B. We proved this right here, right? The sine of one angle equals the sine of the other, and vice versa. So keep that in mind. We also introduced this new symbol here. We haven't dealt with theta before, but this little looks like a 0 with a slash through it is the Greek letter theta. You can just think of this as x. For most angle measurements, instead of using x as our unknown value, you will use theta as an unknown value. So again, we'll just be solving for x or trying to solve for theta when there's an unknown angle. So for this example, we know if angle A is theta, therefore angle B, because of the triangle sum theorem, angle B has to be 90 minus theta, right? So if this one's 30 degrees, angle B has to be 60 degrees. If this theta is 40 degrees, angle B has to be 50 degrees. So therefore, they just plug in this 90 minus x into our equation up here for angle B. So it says the sine of angle A, or theta, right? The sine of theta is equal to the cosine of angle B, or 90 minus theta. Similarly, the cosine of angle of theta is equal to the sine of 90 minus theta. So just keep this property in mind. It'll make a little more sense when, well, we can do a couple examples here. So if theta, so right here, if theta is equal to, 30, right? Therefore, angle B, right, will be 90 minus 30, and that'll be equal to 60. So we can conclude from this that if there's ever a problem where we can punch this in the calculator. We can say that the sine of 30 should be equal to the cosine of 60, and vice versa, right? Why don't we test this in our calculator real quick? So I said that the sine of 30, so sine of 30 equals 1/2 the cosine of 60 equals 1/2, right? So just keep that property in mind. What can I conclude about the sine and cosine of 45 degrees? So in this case, 90 minus 45 is 45, right? So these two will just be equal. Is it possible for the sine or cosine of an acute angle to equal 1? Let me draw a right triangle. By acute angle, they mean not the right triangle, right? Or not the right angle. Is it possible for the sine of this angle to equal 1? In order for it to equal 1, the opposite over the hypotenuse would have to be equal 1, right? Which would mean that the opposite and the hypotenuse are the same value. Is it possible for a right triangle to have a hypotenuse that's the same length as a leg? No, it's not. So it's just not possible. Here are a few more problems. Go ahead and pause here, see if you can solve these ones. Here's your pause screen. All right, so this guy here. We can punch this into our calculator, right? We know that the cosine of 73 degrees is this value, right? So therefore the sine, we don't even need the calculator, sorry. The sine of the complementary angle would be, if you wanted to, you could punch this in your calculator and calculate the sine of 17. But we know that the sine of the complement is equal to the cosine of whatever angle that is. So you could just go straight to this value without using a calculator. Let's try this one. Same sort of deal here. You know that the cosine of 45 degrees is equal to the sine of 45 degrees, which is this value here. Okay, these problems are much more applicable actually. This one says a 12-foot ramp is installed alongside some steps to provide wheelchair access to a library. The ramp makes an angle of 11 degrees with the ground. Find each dimension to the nearest tenth of a foot. So in this case, there's many applications for construction with these guys. Before, we had no way of doing this problem, right? We didn't. We only had one of the lengths. We have two of the angles, so we can figure out the third, but that doesn't help us figure out either of these two lengths, even though it is a right triangle. So now we have a powerful tool. We can actually calculate these things. So we know that the we'll start with we'll do angle A here. We know that angle A is 11 degrees. Therefore, the sine of angle A is equal to the opposite over hypotenuse, right? So x over 12. And then when we set up that equation with 11, x, and 12, we only have one variable, and we can just solve for that one variable. It just becomes an algebra problem. So we can say that the sine of 11 is equal to x over 12. If I have sine of 11 equals x over 12, I need to solve for x. In order to do that, I just multiply both sides by 12. So I have 12 times the sine of 11 equals x. Let's practice punching that into our calculator real quick. 12 times the sine of 11 equals x. If I'm over here and I punch 12 times sine of 11. Oh no, I get some weird negative thing and it's crazy. What happened? Oh, I had it in radians. Make sure you're in degrees. Every time you do this, make sure it's in degrees. So let's try that again. It was 12 times the sine of 11? I forget. Yeah, 12 times the sine of 11. Okay. Sine of 11 equals, this is a little more normal, 2.29 or 2.3, I guess. Oh, look at that. That's the same answer they got. So we're good there. Find the distance y that the ramp extends in front of the wall. We'll do another pause here and let you guys figure that out. So pause. Okay, hopefully you had some values. We're going to substitute in the correct value for angle A, which is 11. We'll substitute in the correct value for AC, which is 12. We know all these values. We can plug it into our equation here for the definition of the cosine of angle A. The cosine of 11 is equal to y divided by 12. Multiply both sides by 12. And then again, we can solve for y just by plugging this into the calculator. Note here, though, that we can kind of imagine parentheses here. The book never uses parentheses. My calculator does, if you notice, though. When we take the cosine of some value that's similar to like squaring it or taking the square root or something like that, if we were to multiply this whole thing by 2, or well, let's say we're doing it by 12, we can't just say that 12 times the cosine of 11 is equal to the cosine of what is it, 131? Yeah, 132. Right? 12 times 11. That doesn't work. We can't do the cosine of 132. We need to treat this this cosine as a single unit here, right? The cosine of 11 is some value. We can multiply that value by 12. That's fine, but we can't just jam this 12 inside our cosine parentheses. We have to figure out what that is first. So we can go to our calculator here, fill it out. 12 times the cosine of 11 gives me 11.8, which should be pretty close to what they get. 11.8. It's probably a little hard to see. There you go. 11.8, and I can see 11.8 there. Cool. All right, here's another one. I'll pause here, see if you can figure it out. Pause. So here we have a ramp. It has to be 8 degrees. We have to get over a wall that's 2.3 feet. So we're going to use the sine function of angle 8 here. We can say that the sine of angle A equals the opposite over hypotenuse, which gives us an equation like this, right? The sine of 8 degrees equals 2.3 over z. This one I'm going to take a second and kind of write out because the book doesn't. Just as a reminder here, we can't just divide both sides by z. This time the z is in the denominator, so we have to multiply both sides by z and then divide both sides by sine of 8. Another way to think of this is we have sine of 8 over 1, and then we can cross multiply. That's another way to do it. Regardless, we need to get z by itself in some way, shape, or form. So in this case, I'll just multiply both sides by z. So I'm going to go times z times z. Bear with me here, these ones cancel. That gives me z times sine of 8 is approximately equal to 2.3. And then I divide both sides by sine of 8 over sine of 8 over sine of 8. These ones cancel. And I'm left with z equals 2.3 divided by the sine of 8, which we can do in our calculator. 2.3 divided by sine of 8. If you have a scientific calculator, you can set it up this way. If you have an iPhone calculator, you'll have to type in 8 first and then hit sine, and it'll just spit out what the sine of 8 is. And then you'll have to do, what is it, 2.3 divided by equals, and it'll remember that value and give you a good value for it. If not, you can always break it down and just write down what sine of 8 is, and then divide that as a separate function. But I get 16.5, which maybe you got? Hopefully you did. Whoops. Okay, cool. 16.5 feet long. Cool. We're good there. We'll spend the rest of our time in class working on this sort of stuff, including all these problems. So have a good day.